From the beginning, Allen Bradley is a story of innovation, from the evolution of carbon discs, and then the motor control side of the business. Then carbon was used in resistors and potentiometers, and we became a major force in electronic components, all derived from carbon. And so the company was innovative in terms of the design of motor controls, all the way up through the series, and then with fixed resistors that would go to the moon and back, and potentiometers that were used in World War II planes, basically in layman's terms, a volume control. But innovation all the way up to PLCs, numerical control, drives, and into today. But it has been 100 years of innovation, creativity, and investment in new products.
You know, the composition resistor, it was kind of a neat thing, because as you go back in the history of Allen Bradley, the two Bradley brothers, Line and Harry, they were making the compression rheostat. That was one of the first products that they had made way back when.
He got the idea he cut these carbon wafers off of throwaway components in carbon street lamps, cut them into wafers and put them in a vise with a insulator on both ends, and connected the wire to both ends, and he found out that he tightened the vise up, the resistance would go down. Loosened it up, the air spaces were a little bigger, the resistance would go up. So he could control the speed of a motor, a DC motor, by doing that.
From that, they then they designed the variable resistor called the Bradley stat. And it's the neatest thing. When you take a look at the early Bradley stats, they had them in automobiles on the dashboard. And they used that to vary the amount of voltage which was being created by the generator, which would be going into the battery. And they had one that said summer, and then they had one for country driving, they had one for winter driving, and city driving. So you could adjust it. Like during the wintertime, you might needed to charge your battery a little bit more. So you rotated the variable resistor to the winter setting, and now you get a little bit more battery charge. Overcharging a battery was bad because it would boil all the water out of it. So that was one of the first usage. Now, of course, the radio, the variable resistor in the radio was a big factor. The volume controls alone. So Department 350 made variable resistors here, and went on for many years. But it was dwarfed in size compared to the Department 310, which was the fixed resistor department. The little powder that came out from the sawings, the little kerf, as you might want to call it, coming off, at first they were probably just throwing the stuff away. Then they discovered that if they mixed that with a clay-like solution, that they could take that carbon from those cuttings, mix it with that clay-like solution, pack it inside of a phenolic tube, and make a resistor that had a given value. It was a fixed resistor. It wasn't variable, it was just fixed. And it turned out that resistor became one of the finest resistors ever made. The United States military bought them by the millions, and world-renowned as far as their quality was concerned.
As far as we know, our testing was so outstanding that companies take Zenith in Chicago, Motorola, others, they had no incoming inspection of our product whatsoever. It was that quality oriented. All of the machinery was developed internally, partly because we didn't want others to know what we were doing, and partly because we had the talent, this Germanic, Milwaukee was the machine shop of the world, and we had the talent within the company to produce these machines.
Yeah, I was in the special machinery department and the plant engineering department, and that was the department who was charged with designing and building all of the special machinery used in the plant. Most of the machinery we used was built for the molding department for electronic resistors. Molding machines, preform machines, all the machines that were done there, and that program went on for many years.
What they would do is they would go to the machine builders and they would say to them, we need a machine that's going to have an output of this many, whatever it was, whether it was a variable resistor, a fixed resistor, whether it was a starter, whatever it might have been. They would go to those folks and say, look, we need this machine, we need to have so many per hour, and they could multiply 7 days a week and 24 hours a day if they wanted to come up with the final end result as far as the quantity being produced. And at that point, they would then put their thinking caps on, their innovativeness or creativeness, and design a machine which was capable of producing that amount of product in that amount of time. So when it was finished, that machine was then probably drawn up at that point. And many times they didn't have a drawing. The machine builder, more like a tool and die maker, was working on this, and they would then devise a methodology in order to do it. And once they would devise that and they'd prototype it, they'd see it work, and it's okay, now let's go ahead and make a drawing of it, and now we will reproduce these machines.
There were plenty of years where the company had higher sales in the sales of resistors, variable and fixed, than they did in the motor control line.
Actually, when the first color TVs came out, we were in almost every one of them. Then the Japanese figured out how to do that with a film resistor and how to get that, and eventually the film resistor took us out of that business.
That resistor business really, was started in 1937, and it just grew and grew and grew. And the profit from the resistor business carried the company and also produced the capital with which to expand.
Eventually, the integrated circuit. Let's face it, the transistor came along, and the fixed resistor, they still make variable resistors, but the fixed resistor days are pretty much over with.
After the war years, Mr. Bradley and Fred Loke decided that the company had to start thinking about more product lines. At that time, it was motor controls and radio sales. And they started investigating different product lines, and that's when radio sales became electronic. And we became electronic because we did go into the industrial and consumer product lines. So that's where electronics came in. The new lines were ceramic capacitors, ferrites, ferrite magnets, resistor networks, and the people that came to work for us were people that knew all of these product lines and were helping us. And there were also plants that were built to cover these product lines.
We concentrated on developing, prior to my time there, products that were basically standard, and they were an improvement over what we had, like limit switches or push buttons or something like that. I think Lynn was off base on that. But the growth was going to be in the new products, apart from anything that we were building at the time. Solid state,
Procter & Gamble wanted a control center, and Fred couldn't see getting into the control center business. But this fellow, who was the chief engineer for Procter & Gamble, and the first control center we built for them was just starters on practically angle iron frames.
Allen Bradley didn't have much in the way of product innovation back then in the control business. As they came up with things in the plant and decided to commercialize them, they started the magnetics business, and that grew out of here. That we had a sonic sifter business for many years. Those were new product innovations. But in the control business itself, mainly Allen Bradley sat back and saw what the other guys were doing and then did it better. Mainly better and smaller, last longer, easier to use, those things that were important to the customer. And back then it worked fine.
We kept changing and bringing out more and more solenoid starters, and we changed the motor control centers, and we changed the whole theory of the automation and the fact that it had to be properly serviced.
We were selling a lot of control to the machine tool builders, Kearney and Trecker and Lamb and all these other people. And gradually, General Electric, which division was run by my brother, incidentally, they'd sell a control and they'd pick up the limit switches and the push buttons and the starters. And I thought, Judas Priest, this is going to be rough, because how the hell are we going to get those incidental little things if they buy the control from GE or somebody else? So it was basically that, to protect the basic control industry, that I was concerned about, and that would be really the main reason why I wanted to push in the NC.
The markets were growing, but the technology was shifting away from electromechanical to electronic and computers in almost every case. And we were way behind the curve in making that transition. The company was quite successful financially. It was doing quite well. But it was obvious if we didn't redirect the company in technologies and markets that the growth was going to slow to a standstill.
We started out with a very, very cumbersome thing that we had gone into. I guess we actually bought from information. It was 3i out of Detroit. Then we went into what we called the PDQ-2.
The first ones that came out, and PDQ-2 was one of those, were too computer-like. They were kind of designed by computer guys to be rugged enough and work on the shop floor, but they lacked kind of the, if you had a computer technician, they'd be just fine. The problem was automotive plants didn't have any computer technicians. They had a bunch of electricians, union electricians. So what you really had to do was, and by the time I'd gotten there, that had kind of sorted out. And now you had programmable controllers that really did look like relay replacers. And the relay ladder logic, which is this specialty language that was created as much for that maintenance electrician, the guy that actually did the maintenance on this stuff, so he could understand it, as anything. And it became one of the big successes of PLCs. They never would have been successful if they'd had to redo all the trades in the automotive or add a trade, so you'd still have kind of the electromechanical guys and the computer guys. Then that would have added too much overhead. So one of the kind of simplistic reasons why PLCs took off was because you could train the same maintenance people that troubleshot relay panels to troubleshoot and maintain these PLCs.
First it was Westinghouse SciPac. And the thing here was your relays, you draw ladder diagrams with little relay contacts in them. But this was a little bit different concept. You had, it was called cybernetics at that time. I think Westinghouse invented that term. But instead of having on and off just switches and putting them together in various ways, you had and, or, not, and memory, the four major functions of a logic control system. Time delay is also in there, but and, or, not, in memory. And you did those with whatever units would make it work that way.
Back at that point in time, if you looked at the catalog, the Allen Bradley catalog, the catalog said, on one of the first 2 pages, said something to the effect that while solid-state electronic component products are good, they're not as reliable as the old electromechanical products. And so that was when I walked in and said, geez, what does this mean in English? And then I had some people explain to me what that meant in English. It was that the electromechanical products made all our profits, and the solid-state electronic stuff down in Cleveland, it was doing good, but gosh, we weren't making money, and did the stuff work? And just the whole state of electronics at that point in time wasn't, as quality-oriented as it is now. So, but you could really see, because we had a lot of customer interaction then, and just looking at the customers' eyes light up when they saw what the PLCs could do for them. I said, something must be going on here, because the customers really like that. And they really liked the company. They loved the electromechanical products. They loved the stuff that was going on with solid state, although they were still whining a little bit about, well, it kind of doesn't work as well as we'd like it to. Well, that was primarily because of the electronics themselves, not the products that we were building. But the solid state electronic components then weren't as good in temperature at that point in time. But so a lot of excitement. You can really see it like I saw it talking to customers.
We finally got to probably mid to late 70s, the 1774, the black box PLC. And that was Otto Struder's design, and really blew everybody out of the water. It came out with The early PLCs, to program them, you had to actually put them in take the big core memory out, which was probably about 1,000 bits, and stick it in it looked like a microwave oven, and program it with a mainframe. Whereas when he came out with the black box PLC, it programmed with a program panel. It was in ladder logic, and that was really our start.
And it was also the first one that went through kind of the cycle of coming out with a product and then enhancing it 2 or 3 times before you abandon the platform, which is also a big part of our history, which is not walking away from the customer's investment, but finding a way to migrate technology forward. Well, PLC was really the first product that really migrated the technology forward. And then from those early PLCs, we ended up splitting into kind of a small, medium, and large family of PLCs. The mini PLC2 was the first small PLC, and then there was a PLC2, and then eventually there was the PLC3, and I was very much involved in the launch and the success of PLC3, which at one point in time we bought out the PLC3, the PLC 220 and 230, and the mini PLC 215, all within a very short period. And this leapfrog we'd been playing with Monicon all along, we all but buried them at that point. We had both a mid-size, a small, medium, and large PLC that was heads above anything they had. And no matter where they came at us, we were able to kind of stay ahead for a long period of time. So it was a wonderful period of history from about 80 through about 84, 85 was a really important time for the automotive. Heavy growth in PLC3s.
Don Davis had gone to the board of directors, or the board of trustees as they were known then, and basically said, we need to be number one in this business. I need $8 to $10 million, which back in 1980, 81, that's a large amount of money that we need to do a bunch of product development. And so then my job was the program manager for all the new products that were coming out. And so we wanted to make sure we designed stuff in because we didn't want this was our next generation of products. So we not only had to clean up the problems we had with our current products, we really wanted to make sure that we designed in as much as we could qual into the new products.
It was also during that period of time that the automotive companies began to spend a tremendous amount of money in their assembly areas or their body shops. And PLC3 was one of those programmable controllers that was selected, and we ended up, as a result of that, of having a huge, huge market share in all of the automotive companies, all the big three here in the U.S.
We developed PLC3s, which at that point in time were like $50,000 a system. And General Motors was so worried about quality that they bought backup systems in all their assembly plants. And after about the first 7 or 8 months, they quit buying them. And we asked them, geez, what's the matter? Is there something wrong? He said, no, your stuff doesn't fail. We don't need backup like we used to need on solid-state electronic products before. So they just did a super job, Roger and Otto Sturger, basically taking us into the new millennium in terms of designing quality in, not trying to test it in.
Well, PLC3 was kind of the first real advanced programmable controller that found a way to take a lot of those computer-like functions and make them work in a plant floor controller. So the PLC3 really kind of set the standard for the industry for years to come. And many of our future products that came as a result of that, which included PLC5, and even some of the features of control logics today kind of had their start in the PLC3. The multiple data types and all that kind of stuff was first kind of invented there. So there was a heavy learning curve, but that PLC could do things that none had ever done before, both in size and kind of scope and instruction set. It was also at that point in time that the whole information capture and control and information integration kind of started. And the PLC3 with its GA module and its data handling capability and whatever, while we had an early version of that in PLC, the PLC3 really was the first to have not just robust sequential control, but also good reporting and the opportunity to get some data back from the process. And it really was the first place we started to really link control and information and integrate them together. Now, the operator interfaces weren't exactly elegant, and so sometimes what you got was a report that printed out on a TI Silent 700 printer, and it wasn't great to look at, but you were getting data back from the process that helped you make it better. And so that was kind of a whole leap forward in control.
We were fundamentally a hardware company. We wanted to maintain being a hardware company, but we had to get into software significantly larger scale than we did before, because PLCs grew up just having plant floor electricians using ladder logic to program them. The way that technology was growing, basically we had to deal with process control, we had to deal with motion control. We had a bunch of people at some point in time said that, hey, all you need is soft PLCs, you don't need any hardware PLCs and all that. So really had to wrestle with that. So I think we did a real good job of spending time with the architecture, sitting down and looking, spent a lot of time in Cleveland. I think Keith Nosbush at that point in time was either run the PLC business, then he became the group guy, did a good job. Keith and I spent a lot of time trying to say, so this control logic architecture was really born during that point in time.
The World Contactor facility came about for a variety of reasons. One, we wanted to become involved in what was called IEC standards, which were smaller contactors and starters and those kinds of things. But there were several ways we could attack that. We could go acquire a company in Europe. We could design our own. But once we came to the conclusion that we would like to design our own, then we had to find an extremely low-cost way of manufacturing those contactors and switches, if you will. And we were in the computer integrated manufacturing business. We were out there promoting that worldwide. It would seem like to us that if we had a factory that ran essentially no people, no paper, no nothing, but put this stuff together all by itself, that would not only give us very, very low costs, but it would give us an example for our potential customers that this light assembly could be done in a peopless, paperless, lights-out factory. But we couldn't go tell these people that that was a good thing to do if the investment was not justified financially. So we worked with Larry Yost and gave him the challenge that he had to come up with a way of designing this factory where it could just, like I said, it could just run lights out. You could get an order from Australia and you could make it the next day in the factory and nobody had to do anything. But it had to have a reasonable return on investment. It was interesting. What we found was that we couldn't have any inventory. If we had normal amounts of inventory turns, like 3 and 4 turns of inventory, that inventory added too much investment and it couldn't justify itself. So Larry and his team went back and redesigned the factory where essentially at the end of any production period, whether it was a day, a week, or a month, we essentially had no inventory. It was all pulled out of here. It was gone through the factory. It was put in boxes and shipped. And so we could erase that normal cost of inventory. That's what pushed it over the top. Otherwise, we would have not gone ahead with it.
The World Contactor facility was the first fully computer-integrated manufacturing facility that would produce 600 contactors per hour to a batch of 1 and ship within 24 hours of the customer's order. It was a phenomenal achievement. And the World Contactor put ourselves on the map, so to speak, to say we can do what we're talking about. At the point before this, we hadn't really put our equipment all together into one large system. And at this point in time, when we had done that, we had proved to the world we can do it. And it is something that we want all of you to see. We want you to all come here, see what we've done, and then walk away with a very, very positive feeling that computer integrated manufacturing is highly productive, and it is also very, very profitable from the bottom line.
The Pyramid Integrator was the first one that took the real live programmable controller world and the real live data processing world, or IT world, and put them together in the same chassis and did integration across the backplane between them. And it came about as much because the trades tried to control their particular space. But it certainly was a breakthrough in kind of the concept of integrating control and information. Technology eventually expanded to the point where the networks got more bandwidth, and now you could link real-live computers with real-live PLCs. And of course, the control logics architecture now is just about as efficient as both in both areas. And so we kind of evolved to the point where whatever you needed, the platform was kind of able to provide for you. And but that's kind of a common evolution of technology. It's just like mainframes turning into multiple personal computers. We had our own evolution. The difference was we were at the center of this, right? I mean, it was us and a couple other competitors that were kind of making these big breakthrough kind of things. So one of the things that we really brought to the manufacturing industry worldwide.
To be able to take DeviceNet, putting that on a network so that when we have a limit switch or a sensor of some type that might be failing, or you might have a condition where the condition around this, maybe the temperature is rising, you can sense that with this system, and it adds to the manufacturing individual who is sitting behind a control panel in a power plant, being able to visually see what is going on within that system, or perhaps it's a chemical processing plant or a paper converting plant, to be able to witness changes going on in the system with our products is phenomenal. Motor protection is one of our big industries where we make a lot of overload relays. We have some very, very incredibly smart overload relays. And those relays are protecting motors, and they're also ensuring that the process continues. Many times a chemical processing plant or a paper converting plant, you can't stop that process. That process must continue. So you need to be able to have the intelligence to know what's going on within that system and be able to verify and correct and prevent failures from occurring before they happen. And our products, because of the intelligent systems that we have, can do that for our customers. So that makes it the next step, the step beyond.